So, of course, discovering those electrons led to many more questions, which is usually how things work. So there's negative electrons in the atom, but we know that the atom is neutral. That means there must be something positive in there. There must be positive charge. So how do the opposite charges, positive and negative, fit together inside the atom? Are there even more fundamental particles and they're all jumbled together? Are they ordered? What's going on? Is an atom a solid sphere and we are just literally taking pieces off the outside? Or is there some internal structure? Lots and lots and lots of questions. So Thomson of the cathode ray tube proposed what's known as the plum pudding model. So this was in England, where people eat something called plum pudding, which we just really don't have in the United States. The closest thing I can give you to plum pudding would be like a blueberry muffin. So we'll call it the blueberry muffin model. So the electrons are the blueberries in the muffin. They're just kind of, randomly distributed. And the whole thing is made up of the muffin part. Okay, that's that positive charge. And then the electrons are inside of that. You have to start somewhere, right? So that's what the model was. So then you test it. So again, we have to do a little sidetrack here and talk very briefly about radioactivity. Some nuclei are unstable, and these little energetic particles just spontaneously shoot out of them. These unstable nuclei are basically falling apart one little piece at a time. That was discovered at the end of the 19th century. Those particles, the radiation, can be used to investigate other things. And so that was important for scientists to be able to probe the structure of the atom. Three of the major types of radiation are alpha particles, beta particles, and gamma rays. Alpha particles are the largest. They're the most massive, and they also have positive charge. And you'll get more on that later in Chem 1B. So you can just forget all of that now. So Rutherford worked under Thomson. Thomson had this plum pudding blueberry muffin model. So Rutherford's doing this experiment trying to show that the model is correct. So he sends these positively charged alpha particles at an extremely thin sheet of gold foil. In the plum pudding model, we've got the mass and the charge just, uniformly distributed through the whole volume of the atom. And so the prediction is that these little particles would just go straight through the gold foil. This is an illustration of his setup. So we have a source of the alpha particles, and there's this beam shooting at this gold foil, and we expect the particles to go straight through. This circle here is a detector, so that when those particles come out, we can see where they went. So most of them did go through, either just straight through or they had a little bit of deflection. But some of them were deflected by a significant angle, and some of them bounced back. That was shocking. About 1 in 20,000 bounced back, and Rutherford said that was about as credible, about as believable as if you'd fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So, you're firing a gun where the bullet is 15 inches. This is big, right? At a piece of tissue paper. And it bounces back? What? This was so surprising. So this led to a new model because this showed that the plum pudding model was just not correct. So from this experiment, he concluded that matter must not be as uniform as it appears. So here's the plum pudding blueberry muffin model. The alpha particles should just go straight through. So he came up with a nuclear model. So we have a nucleus here where most of the mass is, It's extremely dense, and then there's this cloud where the electrons are, and that's mostly empty space. So what happens is most of these particles hit the electron cloud, there's almost nothing there, they go straight through. But if the particle hits the nucleus, that's very massive, the particle has a positive charge, the nucleus has a positive charge, they are repelled, and it bounces back. So it's still maybe a little hard to visualize. Let's think about a volleyball net and airsoft pellets. So you got your little airsoft gun and you're shooting pellets at the volleyball net. Where do most of the pellets go? They go straight through, right? Because there's big openings with these little strings. But what if the pellet hits the string? Does it keep going straight through? No. It might not bounce back and hit you, but at least it's going to kind of stop and fall to the ground. The string is going to stop it. And so that's a little bit what this nucleus was doing. It was something that the alpha particle could not go through, it would bounce off of. So Rutherford's nuclear theory had three basic ideas. Most of the atom's mass and all the positive charge is contained in a small core called the nucleus. Most of the volume of the atom is empty space, and in that empty space we have tiny negatively charged electrons dispersed. No idea yet what those electrons were doing. That's like a whole nother chapter later in the semester. People are still arguing about it. There are as many negatively charged electrons outside the nucleus as there are positively charged particles, which were named protons, inside the nucleus, so the atom is electrically neutral. So that was the nuclear theory. It was very successful. But there was a problem. So hydrogen had one proton in it, and there one electron. Electrons don't weigh much of anything. Helium had two protons and two electrons. So you would expect that helium would be twice as massive as hydrogen. It would weigh twice as much because it has twice as many of these heavier particles. But it was 4 times as heavy. So something was missing. And what was missing is the neutron. So Rutherford and one of his students, Chadwick, demonstrated that mass that they couldn't account for was due to neutrons. Those are neutral particles inside the nucleus. So if we go back to the picture here, there are protons and neutrons in the nucleus, and that's where almost all the mass is, and then the little tiny electrons out here. So neutrons have no electrical charge, they're neutral. Neutrons are neutral. Protons are positive. Electrons have to be the other thing, which is negative. The mass of a neutron is very, very close to that of a proton. So the explanation then for that helium to hydrogen mass ratio of 4:1, hydrogen has one proton and no neutron in it, it has one massive particle. Helium has 2 protons and 2 neutrons, so it has 4 particles. 4 particles to 1 particle gives you that 4:1 ratio. The nucleus is extremely dense. It's an understatement. So more than 99.9% of the mass of an atom is in the nucleus, and yet that nucleus is extremely tiny. The electrons are, we can think of them as being like water droplets in a cloud or water droplets in the fog, right? Clouds are just kind of up there, but we've all walked through the fog, right? We know about fog. So those little droplets of water in the fog have negligible mass. They're very tiny. They're so tiny they're suspended in the air, right? But they are dispersed through a large volume, right? And they prevent you from seeing through the fog. And yet fog is mostly empty space. You can walk through it, right? So clouds and atoms, both mostly empty space. Giving you an idea of relative size. So if the nucleus was the size of a period, then the electrons would be about 10 meters away. So this is 1 meter. So 10 meters, probably like over there at the door. And this is a period, little tiny period. I can't make one that small on the chalkboard. Little tiny period, that's the nucleus, where all the mass is. And then the electrons are way over there. And they are much smaller than the nucleus. So most of it is just empty space. If you could take nuclei and squish them together to make something as big as a grain of sand, just nuclei, take all that empty space out of it, that would weigh 11 million pounds. A grain of sand that weighed 11 million pounds. The nucleus is extremely dense. Very, very dense. Another analogy. So let's say you built some scaffolding, like they build around, buildings for the workers to climb up and build on. This reminds me of an old-fashioned jungle gym. They used to make playground equipment out of just metal pipes, and they didn't have rubber or soft bark mulch or anything. They had asphalt under them, which is better than concrete, but not so much. And kids fell on their heads all the time. The good old days. Anyway, this reminds me of a giant jungle gym. But you see there's a little guy standing here. So this is like super, super big. So we're imagining this. It takes up a whole football field, and it's 100 stories tall, okay? And yet it's just made up of these pipes, and it's really mostly empty space, right? But if you looked at this from an airplane, from a high elevation, it would look like something solid, right? Because like in this picture, we're not looking straight through one of the holes, and so our vision gets blocked by all these little tiny bars. So it looks like it's solid. If this was the size of the whole atom, a football field and 100 stories tall, the nucleus in there would be the size of a little green pea. So how does matter behave as a solid? Why does it look uniform? I mean, you look at this bench top, right? It's hard. And it doesn't look like it's made up of little particles with a lot of space in between, does it? It looks solid to us because that variation in density is on a scale that is way too small for our eyes to see. Because that empty space is inside of an atom, and the atom itself is way too small to see. So when I knock on the table here, it's like taking one of these giant scaffoldings, which is mostly empty space, and knocking it into the other. In spite of them both being empty space, they're not going to just pass through each other. Does that make sense? So matter is mostly empty space, but you can't walk through walls.